Hello guys, welcome back to TechDose, and in this video we will learn about bitsets. You must watch this video completely till the end because no knowledge is much better than half knowledge. In this video we will be looking at what is a bitset, why to use it, where to use it, as well as comparing bitsets with other available options that we keep on using, and we will check on the optimizations which the bitsets provide in terms of time and space when it is compared with the other options which are available to us. Okay. So let's get started. Now first thing we will learn is the representations, and if you imagine like our number 10, which is 1010 in binary, and if you have to represent it, in how many ways can you represent this? In simple terms, if we speak, then we can represent in terms of base 10 number system, which is writing just 10, right? So 10 in base 10 is actually representing 1010 in binary. You can also represent this in terms of array of boolean, where you create an array of size 4 and you say 1 for the set bit and you write 0 for the unset bit. That means writing true or false. Okay. So in this way you can also represent the binary in terms of boolean array. You can also take a vector boolean array where it will perform very similar to an array, but it is not exactly the same. We will learn this in the video itself. We will compare them both. And the last option is through bitset. You have to mention the size of the bitset. It should always be a constant size. Okay, it is not dynamic, and you have to write the decimal number for which you want the binary representation, or you can give the binary string representation directly. If you give decimal, then it will be converted to binary. Okay, so these are the simple things, and we will compare 2, 3 and 4, and we will see why we should go for bitset. Now let's compare the boolean array with the vector boolean and the bitset. So if you want to set the third bit, that means index 2 bit, then you can simply write a at 2 equals to true, where a is the array, right, the boolean array, and this is the simple array access, and this works the same. I mean, it is the same for vector as well as it is the same for bitset too. Okay, so all of them feel exactly the same. And again, if you want to check if array at index 1 is true or false, then you can check it simply as if they are array of booleans. Okay, so you can check all these three in the same way. You can unset them in very similar way. But where they differ is in the boolean array, for every flag 1 byte is consumed. Okay, and for the vector boolean, it will consume only 1 bit per flag. Therefore you know that 8 bits combine to make 1 byte. Therefore this will be 8 times more space efficient as compared to the boolean array. And the same goes for bitset. In the bitset you have 1 bit per flag. Therefore again this is 8 times space efficient as compared to the boolean array, right? So this is in terms of space complexity. We will see how they differ just in the next slide. And if I talk in terms of runtime, then the slowest one will be the vector boolean. It is the slowest. The boolean array is faster than the vector boolean, and the bitset has the fastest speed. Okay, I mean the bit operations are inherently faster, and we shall compare now all the space and time complexity reasoning. Let's take an example and try to understand our previous comparison. So let's say that we are given 2 containers. So it will not be items, it will be containers. So let's say we are given containers A and B, and we need to find the count of common items. So container A has 1, 2, 4, 6, and let's say container B has 2, 3, 4, 5, and we have to answer about what are the common items. And let's assume that the constraint says the items are in the range of 0 to n or 0 to n minus 1. In this case it will be 0 to 6. Now if you already know this, then you can create a boolean array simply, right? Boolean array, and you can just make it a size from 0 to 6, and you can mark what all items are present and what all are not present. So if you check for A, you check it out here. 1 is present, so we will set this bit. 2 is present, so we will set this bit. Similarly for 4 and 6, we will set the bits for 4 and 6, and the other bits will all be unset. It will all be 0. And similarly if you compare, this is B's representation, right? Now if you want to find out the common items between A and B, then you can just iterate over this entire array, and you can find out wherever you have common set bits for both of them. So in this case these are for 2 and 4, and therefore you can say that there are 2 items in common, and you could do this in order of n time. Okay, so this is the simple way in which we will declare the runtime. If you look at it in terms of bitset, then the bit set will be declaring some size. In this case I have just declared 8 size, you can declare 7 size too. If you declare 8 size, then how do you represent A in this case? Now bit set always stores the representation from the least significant bit to the most significant bit, where the least significant bit is always to the right hand side. So you see that do we have 0? We don't have 0, so we will have unset bit here. The set bits will only go for 1, 2, 4, 6. You check it out. For 1, 2 and 4, 6 we will have set bits, and for others we will not have set bits, right? And similarly we can represent B. Now if you want to find out the count of common items, you can just take a bitwise AND between A and B, and the set bits will only be present at those positions wherever you have set bits. Okay, so simply you can find it out using the built-in pop count which is present in the C++ library, or you can just iterate over it and find the set bit count. Okay, if you use the built-in library or something similar, then it will work 32 to 64 times faster as compared to the boolean array, and this will actually depend on if your computer architecture is a 32-bit system or a 64-bit system. So in 64-bit system you can perform 64 operations in order of one time parallelly, and so that is how the speed up happens in case of bit operations. So you can see that bit operations are inherently faster, right, on runtime. Therefore try to use bitset if you want to avoid getting TLE. And now in this example I think it is clear that bitsets are faster than the boolean arrays, right? Now let's look at the other example, and we will now compare the boolean array with the vector array, because I said that the vector array is the slowest. So if vector array is slower than boolean array, then I can say that vector array will be slower than the bitsets. Okay, so let's take an example again. If you look at the boolean array, when we declare boolean array of size n, it will be of fixed size. So this is also a constant here, right? Now in this case 1 byte stores 1 flag, so this is very simple. If I declare an array of size 4, then this is how it will get declared, and if I want to set array at 2 equals to false, then this will be overwritten to value false. The random access on array is O1, and there is no complexity involved because you know the starting position and every size is exactly the same. So it is one of the fastest operations, right? Random access on array. So we have seen the boolean array. Now let's look at the vector array. Now in vector array it stores 1 flag in 1 bit. Okay, so 1 byte has 8 flags. That means 1 bit will store 1 flag. But we will access it just like the boolean array. Whenever we write a at 2 equals to true or false, we just imagine it writing like the same whether you take boolean array or vector array, right? So we at a user level do not imagine the low level details, but actually the low level details are different for vector and boolean. So let's take an example. If you want to set a at 9 equals to true, that is the given instruction from the user, then the compiler will find out the byte where which byte are you looking at. So the byte number will be found by giving the position divided by 8, and it will say 1, right? It will say 1. That means it is byte number 1. That means the counting starts from 0. So 0th byte and first byte. So we are looking technically at the second byte. Okay, so this ninth flag will be present in the second byte. How is that? 0, 1 and so on till 7 will be present in byte number 0, and then 8, 9 and so on till 15 will be present in byte number 1, right? So this 9th position will be present in byte number 1. After you have declared which byte you will be present in, you have to find out which bit it is there in that byte, and you can find that by doing mod of 8. So you can do mod of 8 and find the remainder, that will be 1. So this is technically your 0th position in the byte number 2, and this is the position number 1, and similarly the last position will be position 7 when you take the relative positioning inside the same byte. Okay, so you see that all this kind of decoding is happening, that we are doing a at 9, and so first they are finding out which byte number, and then within the same byte number which bit number. So in this case you will find that the second bit of the second byte is the actual position, and once that is determined we will change that bit. Okay, the vector will change that bit and then set it, and then it will notify that the operation is done. So since all these conversions are required, extra logic has to be run. Therefore it is slower on runtime as compared to the boolean array. So in terms of speed we can see that bitsets will be the fastest, and boolean array will be faster than the vector array, right? So I hope this should be clear by now in terms of space as well as time. In terms of space, bit sets are the most space efficient along with the vector array, but boolean array is taking 8 times more space. But in terms of time, bit sets are the fastest along with the boolean array, but vector boolean array is the slowest. But if you consider many operations like union operation, intersection operation, then you will find the real use case of bit sets where this will always shine and it will always outperform the boolean array as well as the vector boolean array. So let's look at some examples. Some use cases which you can see is optimizing the space and time complexity for storing the visited array in the graph problems. You can just try it out. The second use case is you can try out intersection between two sets or two lists, or union between two sets and two lists, or many other operations which can be performed by doing bitwise operation between two lists or two sets. Okay, all these operations will be highly optimized in terms of speed if you use bit sets. Now you can also try to make adjacency list in graph. Yes, it is possible with bit set. So I have given you one example. Even though I have written here map, you can take unordered map, and this is like the node, and this is the list of nodes to which it is pointing out to, or maybe the adjacent node. So the adjacent node of 0 is 1 and 3, adjacent node of 1 is 2, for 2 the adjacent node is 0 and 2, and for 3 the adjacent nodes are 1, 2, 3. And if you have to represent it in terms of bit set, then you look at it. For 0, since you know that total items are till 3, that means 0 to 3, right? I will know the number of vertices available, so it will be from 0 to n minus 1, that is 0 to 3. Now when you know that, then you can declare the bit set size initially while declaring the map, okay, while declaring the adjacency list, and then you can declare bit set of size 4. In this case again, when you declare size 4, it will be from right to left because the least significant bit is on the rightmost side. If 0 is following 1 and 3, that means if 0's adjacent nodes are 1 and 3, then you set that 1 and 3 bit here and you unset all the others, right? And in the similar way, you can follow for 1 is only following 2, that means 1 has adjacent node as 2. So you can just set this 2 and unset rest of the other bits, and you can follow the same for 2 and 3. So this is how you can have the adjacency list using bit set. Now what is the use case of this? Let's say that my question involves finding common adjacent item between pairs. So if you want to find out what are the common adjacent items between 0 and 2, so you may have to you may have to iterate over the items and check it out if they are common or not. But you can do it with Bitset in a very fast speed by doing 0 ANDed with 2. That means adjacency list at 0 ANDed with adjacency list at 2. So you have to write adj at 0 ANDed with adj at 2. Right? If you do that, in this case the output will be 0, because if you AND this one with the third one, then the output will be 0. There is nothing in common. So this will show that there is nothing in common, and this will be very fast, as we had already seen how it is optimizing on time. If you want to find out the common items between, let's say 0 and 3, then you will do adjacency list at 0 ANDed with adjacency list at 3, right? And your output will be 1 0 1 0, because this item is in common and this item is in common, whereas the other items are not in common. And now you can apply the built-in pop count to count how many items are in common, or you can just iterate over it and find which all items are common. So these are few example use cases of bit sets. Now just to summarize, the bit sets behaves just like an array of bits, and operations are very similar to array of bits. It is space optimized, so it has 1 bit per flag, and runtime is very much optimized because if it is 32 bits architecture, it will make it 32x faster than the boolean array, and if it is 64 bit architecture, then it will make it 64 times faster. Bit operations are inherently faster, as you must be knowing. Everything on computer architecture is faster if it is written in terms of bit. Otherwise your code will be converted into bits and then it will be run. Okay, so you are saving that conversion step, therefore bit operations will always be faster. I would like to announce about our live training programs, data structures and algorithms, which is interview dose, and system design, which is design dose. If you are looking for making a switch from service to product based, or even make a product based to product based top tier switch and aiming for your dream company, this is the best curriculum you can ever join. I'll be your mentor throughout the cohort, and I will help you clear all your doubts in the one-on-one sessions. You can know more about this by querying us on the WhatsApp number, or you can also visit our website techdose.co.in. So this was the basics about Bitset. I hope you were able to understand it. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.